Well, hello retro computing enthusiasts. Mike here, welcome back to my channel and episode 5 of me working on the JAZ80 breadboard retro computer with the Z80 processor. Wow, 5 episodes. We've gotten pretty far on building this computer. This is the computer that I always wanted to build back when I was in college 40 years ago, so I could have my own computer, because I couldn't afford to buy one. Well, it turned out I was too busy and too broke to even afford to buy the parts to build my own computer back in college. The technology marched on and the Z80 wasn't a thing anymore, and well, I kind of forgot about it for a while. But, you know, now that I'm retired, I have some more time on my hands than I did back then, and I'm slightly less broke, although I wouldn't call myself rich by any means. You know, I got the idea of, well, maybe I can build the computer I always wanted to build back in college. Get it up and running. So we've come a long way. Back in the last episode, we got the SIO chip here installed and wrote some test code. We actually got a hello world message out of this thing. That was a major milestone, I think. So we're almost done with upgrading this to what I'm calling level 1. We'll take a close look at the schematic diagram here, and I'll show you what we have left to do. Okay, here's our level 1A schematic. I made some revisions in the last video. We redid the reset circuit, and we got the SIO in and working. But we're not quite done yet. We're missing this piece right here, the PIO. So we're going to install the PIO chip today and get it working. It's pretty straightforward. We've just got to drop the chip in and connect basically all of the lines on this side that we need, and power and ground. And then we've got to write some code to initialize it, and then some code to use it, because we can initialize it, but if we don't send any data out to the ports or read any data in from the ports, well, it's just sitting there generating heat and not doing anything. So we'll have to write some test code to make sure that we've actually got it initialized correctly and we're using it. So we'll do that later too. Now, some of you out there may be wondering why I'm bothering installing a PIO chip when we have the diagnostic port here, when we can use it as a parallel port. Well, there's a couple of reasons I wanted a separate PIO chip. First off, we get bidirectional I/O with the PIO. This is only an output port, okay? That's all it'll do, is it'll output. So we can have inputs as well as outputs here on both of these. And we get 2 ports with this chip. So we got port A and port B, and each port has 8 bits on it. So that's a fair amount of I/O. Plus we have a couple of handshaking lines for each port. So this could be a very useful chip. Plus, not only that, this chip being a part of the Z80 family of peripheral chips handles the Z80 interrupt scheme, daisy chain interrupt scheme, very well. So, you know, if we decide to use interrupts in the future, we can just wire this in the interrupt daisy chain and give it whatever priority we want by its position in the chain. Z80's level 2 interrupts are super simple with the Z80 family chips, and we're going to have several. We're going to have the CTC, the SIO, and the PIO. So they can all generate interrupts in the future and be handled very easily. Now, I did consider using an Intel 8255 here instead of the Z80 PIO chip. And one of the advantages of using the 8255 is you get a few more lines. Maybe 2 more I/O lines, that's about it. But the disadvantage is it doesn't work with the Z80 interrupt scheme. You'd have to come up with something completely different for that. So I just decided to go ahead and use the PIO. I don't really think going to need that many extra I/O lines. And another reason I don't want to use the diagnostic port for I/O is I have plans for the diagnostic port in future iterations of the JAZ80. Once we get up to level 2, level 3, we'll be using the diagnostic port, not so much as a diagnostic port anymore, but as an output port where these bits coming out here modify the behavior of the hardware in some way. We may implement bank switching in the RAM. I mean, we've got 128K of RAM. We're only using half of it right now. We may even up that amount of RAM. We may go to 512 or a megabyte. Who knows? And we could implement bank switching with these spare lines. We can turn the EEPROM off with these spare lines, although I have another way of doing that too. And they could come in handy for modifying the hardware behavior in lots of different ways. They could come in handy for once we have some sort of mass storage in here, we may need a few lines to twiddle bits on that. So yeah, I don't want to use the diagnostic port for I/O. And then another thing people might be asking is why? What are you going to do with it? What do you need all those I/O lines for anyway? Well, suppose I want to hook up like an old school parallel printer or something. I might need, a port for that. Suppose I want to blink some LEDs. Suppose I want to have inputs, sensing switches or whatnot, analog to digital conversion. There's all kinds of stuff that this would come in handy for in the future. I like my computers to be able to interface to the real world, not just sit, a little box all by themselves doing their own thing. I want them to, be able to talk to the equipment around them. And, well, this will give me some parallel ports for that. Plus, up here we've got a spare serial port that's not being used right at the moment. So we've got some possibilities for interfacing with other equipment down the road, parallel and serial. So that's why I'm putting in the PIO chip. Let me know what you think in the comments. Would you have gone with the 8255? Or would you have gone with the PIO? Or would you have, gone with something else like the 6822 or something like that? Let me know. I'm interested in what you would have done if you were designing the JAZ80. Or if you're following along at home and thinking about making modifications to my design, what would you do differently? So let me know. Okay, so basically all that's left to do to achieve full level 1 on this computer is get the PIO chip installed. So, well, we've got some board real estate here that's been untouched. So there's enough space up here. In fact, I think I'll put the PIO chip right above the SIO chip here, because it needs most of the lines that are already going to the SIO chip. It needs the data lines, the address lines, and read, M1, and, IO request. The only line that's the only line it needs that's going to be a long run is going to be going all the way over here to the IO address decoder chip. So that's going to be a fairly long run, but I think we can make it work. So I'm going to put the PIO chip up here, and let me get it out of my IC chip repository here. Let's see, here it is. There's PIO chip. Z80 PIO, and I think I'm going to put it right in here. Like that. Now all I got to do is wire it up. And then we'll write some test code and see if we can at least blink an LED with it later. Okay? So let me get to wiring. Alright, I think the first thing I'm going to do is run the 8 data lines from the PIO chip here over to the SIO chip here. And that's going to be a fairly short run. So, yeah, let me get that done. Then we'll tackle some of the other stuff. The address lines, M1, IO request read. Oh, it needs the system clock too. I forgot about that. So, yeah. So we'll tackle all that stuff later. Let me sort out the 8 data lines, because they have them split between one side of the SIO and the other here, sort of staggered in a weird order. And then they're doing the same thing with the PIO up here. But again, it's in a different order. It would be nice if they had all these Z80 family chips, if they had laid out the data and address lines and some of the other control lines on the same pins on each chip. That would have been really nice, but you know what? I think it's probably a little late for that. Probably the engineers who designed this thing are probably either long retired or long dead. Okay, let me get to wiring. Okay, look at this rat's nest of wiring. This is what I was complaining about with the Zilog engineers not getting the pins the same on all their interface chips. I mean, why not? I mean, you would think just, reroute things on the die a little bit or reroute them inside the package. It would have made life a lot easier for the people laying out circuit boards back in the day if they could just daisy chain the data lines to the same pins on each peripheral chip, and then the address lines and the control lines and whatnot. So I don't know why it's like this. So I've got the 8 data lines and 2 address lines run from down here at the SIO up to here at the PIO. I still have the control lines, the chip enable line, and the clock line. Oh, and I need to get power and ground in there too with a decoupling capacitor, so I will get to work on that. Yeah, it's a mess. It is a mess. Routing the lines on the PC boards back in the day must have been a nightmare without auto routing. Okay, let me get back to work. I have double checked this all twice just because it is so freaking confusing. Nothing matches up between here and here. It's all crazy. So, and we've already determined in previous videos that I am not Ben Eater when it comes to wiring. So, on the other hand, with them all spread out like this, it's fairly easy for me to trace and double check that everything's going the right direction. Maybe once it's all wired up nice, once it's all wired up correctly, I can maybe lay them down and bunch them up a little better so it's not quite so crazy rat's nesting. We'll see. But let me get back to wiring. Okay, all the rat's nest wiring is completed and double checked. I think it's all right. Now we need to write some code to enable the PIO. But we also need to know whether we've actually succeeded in getting it working or not. We need to know if we're getting any kind of output on it. So I have added an LED over here and a dropping resistor, and I have run that over to port A, pin 0. So the 0 data line on port A. So if we toggle that line in our software, we should get that LED blinking. So let's write a little bit of software and see if we can make that happen. We'll just add on to what we've already got for the CTC and the SIO. We'll just add some code for initializing and outputting data to the PIO and see if we can get it working. Okay, time to write some code and see if we can get this new PIO chip we've installed up and running and doing something. So we're back in my favorite online Z80 assembler, asm80.com. Love this site. And you'll recognize a lot of the code in here because, well, we've got all of our Hello World code from last time in here. I've just added some stuff to it to work with the PIO. We got the diagnostic port equate, the CTC equates, CTC divider equates, SIO equates, and then down here's the first new code. This is the PIO equates. So these are the addresses of the PIO ports. And like a lot of the Z80 family chips, they have a control port and a data port on the PIO. So we've got port A data, port B data, port A control, port B control. Very similar to the SIO. So, and this is where they are in the I/O port map for the JAZ80, ports 4 to 7. So we've got the equates out of the way, and then nothing much happens that's new. You know, we're going to start up the program, disable interrupts, not that we're using them anyway, set up the stack, We're going to initialize a CTC like before, and then we're going to output a 1 to the diagnostic port. We're going to initialize port A of the SIO. Then we're going to write a 2 to the diagnostic port. Okay. Now here's the new code. So we're going to call PIO init. And I'll show you pipe PIO init in a second. And then after we return from that, we're going to write a 3 to the diagnostic port, and that'll tell us that we have gone through all of our setups and the system is up. Say hello, we've seen that before. And then blink. This is some new code too I'll talk about in a second. But let's go down here to the PIO init. It's very, very simple. Basically what we're going to do is we're going to put port A of the PIO into output mode. And to do that we have to write 0f hex to the PIO-A control register. Okay, so we're going to load 0f hex into the accumulator, and then we're going to output that to PIO-A control register. And if we go and we have a look at the PIO technical manual, what we're doing here is we're outputting this to the control register, 1111 or F hex over in the lower 4 bits signifies that we are sending a mode word. And then the mode word up is the 2 high order bits. So we want mode 0 for output. So 0, and these 2 bits really don't matter. They could be anything, but we're just going to keep them at zeros. So sending 0F hex out to the A control port for the PIO will put the A port in output mode. So that's what we're doing here. That's it. That's all. Now the PIO has lots of different modes. It's got 4 different modes actually, and each port can be in a different mode. So we're only setting up the A port, and we're just using simple output mode. You can have input, you can have mixed input output, and what's the other mode? Control. Bidirectional with control. So you know, we're just doing a simple output port here, okay? So once we have the port set up and we do our say hello thing out through the SIO again, we're going to output HELLO space WORLD exclamation point out the SIO again, just like we did in the last video. Haven't taken that out, it's still there. We're going to come down here to this section called blink. And what we want to do is we want to blink an LED on output port A of the PIO, just to make sure we've hooked it up right, we've programmed it right, and it's working, okay? So what we're going to do is we're going to XOR A, which is basically going to set all the bits in the accumulator to 0, and then we're going to output the accumulator to PIO-A data port. Okay, and what we just wrote there should appear on the LEDs, which would be nothing because you know it's all zeros, so they'll be out. But then we're going to increment A, basically add 1 to it, and then we're going to load a number in the HL register, and we're going to call a delay. And we've seen this delay routine before. If I scroll back down here to the bottom, we've seen this delay routine before. We've used it in the past with just our LED scanning program, just so that the LEDs scanned back and forth across the diagnostic port slow enough for us to see them, and they didn't all look like they were on all the time. So basically all this does is it counts down by decrementing HL until it gets to 0. And then it returns to where it was called from. So we're going to load 7FFF into HL, and we're going to call delay. And then when it comes back, we're going to jump back up here. We're going to output what's in the accumulator, which is now 1, to the port, and the low order bit should come on. And then we're going to increment A, and we're going to go through delay again. We're going to come back up here. We're going to output A to the diagnostic port, and now bit 1 should come on, because bit 0 would have been on before. Now bit 1 will come on, bit 0 will go off, and we'll come down here. We'll increment A, and we'll go through all this. and then we'll output it again, and this time bits 0 and 1 should be on, because that's 3. And this is just going to keep going. All right, but I've only wired up one LED, and that's wired to bit 0 on the output port. So what we should see, if this code runs right, is we should just see that LED blinking on and off, on and off, on and off, as this code executes. Okay, what's happening on the other 7 bits, we're not going to see. But on the low order bit, we should see just blinking on and off, and that'll tell us things are working. Okay? So I hope this is all understandable. If you have questions, leave a comment. This is really not all that complicated code-wise. Okay, time to see if our code works. Let me pull out the EEPROM that had our old Hello World code in it and put in this EEPROM, which has, well, the Hello World code in it, plus the PIO setup code and the code to make the LED blink. And we will turn it on and we'll see what happens. And I will record the screen on the computer, laptop computer too, so we can see if we still get our Hello World message. Want to make sure we haven't broken anything and everything still works, okay? So here we go. Look at that. It's blinking. And there's Hello World on the screen. All right, it's working. It's working. Great. So, you know, this LED is blinking simply because I am incrementing a counter and sending that data out to the I/O port here. If I were to put in 8 LEDs instead of just the 1, we should see it counting up. I think I'll do that just to make sure it's working the way it's supposed to. Okay, rather than using 8 individual LEDs, I used an LED bar. It's got 10 LEDs in it, but I'm only going to use 8. They're all hooked up to the 8 output lines of port A on the PIO. So let's turn this back on and see what happens. Hey, look at that. It looks like everything's working the way it's supposed to. I'll let this run for a while and just make sure all the 8 LEDs are working. I may speed it up a bit. Yes, all 8 LEDs are on at some point. So it's working. Cool. Okay. So basically we have achieved level 1 on the JAZ80. Finally. Yay. Okay. So we're pretty much where I wanted to go with this at this point. There's more stuff I want to do with it in the future, but we'll leave that for the future for now. I think what we need to work on now is getting some decent software on this thing so it can do something useful other than blink some LEDs and say hello world onto my terminal. I need to work on getting a monitor on here, and hey, maybe basic too. Okay, that would be beautiful if we could get a decent monitor on here in basic. Now, I wrote a monitor for another project on this channel, the Teletext System Master, and I modified it to work on yet another project on this channel, the Nabu computer. So I think I can modify it without too much trouble at all to work on the JAZ80 here. The JAZ80 is actually very similar to the Teletech in that I am using the Z80 peripheral components, the CTC, the SIO, and the PIO. Those are all on the Teletext System Master. So I had to write code to initialize and use them. I think I can modify it pretty easily to get it in here. And I managed to incorporate Grant Searle's BASIC into my code as well. So we should be able to do that here as well, I think. So let's take a quick look at the monitor I produced for the Teletext System Master and see what it's going to take to modify it to work with the JAZ80 breadboard computer here. So if I turn on the S100 box over here, there we go. System Master's up and running on my JAZ80 Mon version 0.9.01. For the Teletext System Master, as I said before, this is a little specific to the System Master. We've got a fairly short list of commands here because I only have 2K to work with. But it is extensible by loading other files in off of the computer here. Like I can extend it by loading BASIC in as an Intel hex file, but I have to load it first. So, you know, if you load it, then the BASIC command works. We got memcopy, copy bytes from origin to destination, dump a 256 byte block of memory. We can do that. Let's dump some memory here. Origin, we'll just start at 0. So there's 256 bytes. The first 256 bytes of memory were in the ROM there. And if you go yes, you get another 256 bytes, and so on, as long as you keep saying yes until you say no, and then you wind up back at the command menu. You can edit memory. So let's do that. Let's go E for edit memory, and it'll ask you the address, and we'll go somewhere up in RAM. Let's go like 7,000 hex. We're up in RAM there, above the EEPROM. And okay, well 9D. Well, we can make that. Let's make it 00, 01, 02, 03, 04, 05, 06, and let's say 07, 08, 09. Okay, and then you can just keep up doing this. It'll show you what's in the RAM position, and then it'll allow you to edit it if you want to. If you don't want to edit it, you can just hit enter and it'll show you the next position, next. You can edit or not, your choice, until you hit X, and then you're out. And let's see, if you want to go back to the command menu, you can just hit H. But let's dump that now. Let's dump that section of memory. That was 7,000 hex. So yeah, 01, 02, 03, 04, 05, 6, 7, 8, 9. Yep. So that works. So no. We got some other things here. We can jump to an address and execute it. So if you load a program into memory, somewhere up in RAM, you can jump to that address and execute it. I've demonstrated that in previous videos. I don't have anything else loaded in RAM, but if we jump to 0000, we'll just restart the monitor. So that works. Help just loads, help or H just reloads this screen. We've got hex load, which you can load in Intel. You can load a program in Intel hex format into the computer and then execute it. That's how I get BASIC in. You can get lots of different programs in that way. Also have a binary load program where you can just load binary into an area of RAM and then jump to it if you like. Port scan. I thought I took that out of there. I'll have to amend this. There might be a new revision before it goes on to my blog, because I took port scan out. Port scan is a tool for scanning all of the I/O ports in the system. It's helpful for mapping the configuration of an unknown system, but the System Master, I have all the specs on it, so I don't need that. And it tends to crash the system as soon as it touches the configuration register in the System Master. It crashes it. So I took that out, but apparently it is still on the menu. So I'll take that out. We got import, where you can read a byte from an I/O port. We got outport, where you can write a byte to an output port, and we got bdump, where you can dump binary data from memory into your terminal. So that's all we've got. There's not much room left in that 2K EEPROM. I could probably optimize the code a little bit and make some space for some other functions. Alright, so what we have here is the code for the monitor that I wrote for the Teletext System Master. And there's a lot of code here in spite of it fitting in only 2K of EEPROM on the System Master. There's a lot of stuff here. Now I have a lot more room with the JAZ80. I can put a lot more stuff in there, but I'm going to start with this, okay? I'm going to modify this code, And it should be fairly straightforward. Haha, famous last words, but it should be. So all these equates I have up here at the top of the code, I think if I change them to the equates that we have in our PIO setup program here, which by the way should be on my blog by now, if you want to download this and test it in your own version of the JAZ80. I think if I cut and paste all these equates into the monitor for the Teletext System Master, separate file of course, and make some other necessary changes. There is some code here that's specific to the System Master. I'm going to need to get rid of that and make a few other changes. But yeah, I think I can adapt this to work fairly easily. I think I can adapt this to work on the JAZ80 breadboard computer. And this will give us a lot more functionality than we have now, where we're basically just blinking some LEDs and saying hello world. So we should be able to do a lot more. Plus, should be able to get Grant Searle's Basic on here too. We should be able to turn the JAZ80 breadboard computer into a decent machine here. So I think to keep this video from getting too long and unwieldy, I will do that off camera. And in the next video, once I've got it working, we'll come back and we'll take a look at what new functionalities we've added to the JAZ80. So I think I can do that. I think I can do that fairly simply. It's just going to take me a little time to modify the code, do some testing, make sure it works, and then we'll be back and we will explore the capabilities of my JAZ80 monitor and hopefully get Grant Searle's Basic up and running on this thing too, and maybe play some old vintage basic games on it. That would be nice. So I think I'll end this video here, and in the next video we should have some decent software to load onto the JAZ80 and try running some stuff, okay? So I hope you found this video a little bit interesting, educational, informative, inspirational. Build your own computer. It's not that hard. If so, give it a like, give it a thumbs up, and subscribe to see my future videos where we should have this running as a decent computer in the next video at least. And then I have more upgrade plans for it in the future. We're not done with the JAZ80. Eventually, I want to take this to level 2. And maybe there'll even be a level 3. We'll see. So subscribe to see those future videos, and check out my main channel where I break down old e-wastes to recover the gold and silver from them, but not everything gets broken down. A lot of these chips came from e-waste over here too. So yeah, I saved the good stuff for projects on this channel. But check out that channel. You might find something interesting there. And I will see you in the next video. Thanks a lot for watching this one. Bye.